A giant meteorite boiled the oceans 3.2 billion years ago. Scientists say it was a fertilizer bomb for life. A massive space rock, estimated to be the size of 4 Mount Everests, slammed into Earth more than 3 billion years ago, and the impact could have been unexpectedly beneficial for the earliest forms of life on our planet, according to new research. Typically, when a large space rock crashes into Earth, the impacts are associated with catastrophic devastation, as in the case of the demise of the dinosaurs 66 million years ago, when a roughly 6.2-mile-wide, 10-kilometer asteroid crashed off the coast of the Yucatan Peninsula in what's now Mexico. But Earth was young and a very different place when the S2 meteorite, estimated to have 50 to 200 times more mass than the dinosaur extinction-triggering Chicxulub asteroid, collided with the planet 3.26 billion years ago, according to Nadia Drabin, assistant professor of Earth and Planetary Sciences at Harvard University. She is also lead author of a new study describing the S2 impact and what followed in its aftermath that published Monday in the journal Proceedings of the National Academy of Sciences. No complex life had formed yet, and only single-celled life was present in the form of bacteria and archaea, Drabin wrote in an email. The oceans likely contain some life, but not as much as today, in part due to a lack of nutrients. Some people even describe the Archean oceans as biological deserts. The Archean Earth was a water world with few islands sticking out. It would have been a curious sight, as the oceans were probably green in color from iron-rich deep waters. When the S2 meteorite hit, global chaos ensued, but the impact also stirred up ingredients that might have enriched bacterial life, Drabin said. The new findings could change the way scientists understand how Earth and its fledgling life responded to bombardment from space rocks not long after the planet formed. Uncovering ancient impacts. Early in Earth's history, space rocks frequently hit the young planet. It is estimated that giant impactors, greater than 6.2 miles, 10 kilometers, across, pummeled the planet at least every 15 million years, according to the study authors, meaning that at least 16 giant meteorites hit Earth during the Archean Eon, which lasted from 4 billion to 2.5 billion years ago. But the fallout of those impact events isn't well understood. And given Earth's ever-changing geology, in which massive craters are covered over by volcanic activity and the movement of tectonic plates, the evidence of what happened millions of years ago is hard to find. Drabin is an early Earth geologist intrigued by understanding what the planet was like before the first continents formed and how violent meteoritic impacts affected the evolution of life. These impacts must have significantly affected the origin and the evolution of life on Earth. But how exactly remains a mystery, Drabin said. In my research, I wanted to examine actual hard evidence, excuse the pun, of how giant impacts affected early life. Drabin and her colleagues conducted fieldwork to search for clues in the rocks of the Barberton-Mkandjua Mountains of South Africa. There, geological evidence of 8 impact events, which occurred between 3.6 billion and 3.2 billion years ago, can be found in the rocks and traced through tiny meteorite impact particles called spherules. The small, round particles, which can be glassy or crystalline, occur when large meteorites hit Earth, and they form sedimentary layers in rocks that are known as spheral beds. The team collected a range of samples in South Africa and analyzed the rocks' compositions and geochemistry. Our days typically begin with a long hike into the mountains to reach our sampling locations, Drabin said. Sometimes we're fortunate to have dirt roads that bring us closer. At the site, we study the structures in the rocks across the impact event layer in great detail and use sledgehammers to extract samples for later analysis in the lab. The tightly sandwiched layers of rock preserved a mineral timeline that allowed the researchers to reconstruct what happened when the S2 meteorite hit. Waves of destruction. The S2 meteorite was between 23 and 36 miles, 37 and 58 kilometers, in diameter as it struck the planet. The effects were swift and ferocious, Drabin said. Picture yourself standing off the coast of Cape Cod, in a shelf of shallow water, Drabin said. It's a low-energy environment, without strong currents. Then, all of a sudden, you have a giant tsunami sweeping by and ripping up the seafloor. The tsunami swept across the globe, and heat from the impact was so intense that it boiled off the top layer of the ocean. When oceans boil and evaporate, They form salts such as those observed in the rocks directly after the impact, Drabin said. Dust injected into the atmosphere from the impact darkened the skies within hours, even on the opposite side of the planet. The atmosphere heated up, and the thick dust cloud prevented microbes from converting sunlight into energy. Any life on land or in shallow waters would have felt the adverse effects immediately, and those effects would have persisted from a few years to decades. Eventually, rain would have brought back the top layers of the ocean, and the dust settled. But the deep ocean environment was another story. The tsunami churned up elements, such as iron, and brought them to the surface. Meanwhile, erosion helped wash coastal debris into the sea and released phosphorus from the meteorite. The lab analysis showed a spike in the presence of single-celled organisms that feed off iron and phosphorus immediately after the impact. Life rapidly recovered, and then it thrived, Drabin said. Before the impact, there was some, but not much, life in the oceans due to the lack of nutrients and electron donors such as iron in the shallow water, she said. The impact released essential nutrients such as phosphorus on a global scale. A student aptly called this impact a fertilizer bomb. Overall, this is very good news for the evolution of early life on Earth, as impacts would have been much more frequent during the early stages of life's evolution than they are today. How Earth responds to direct hits. The S2 and Chicxulub asteroid impacts had different consequences due to the space rock's respective sizes and the stage the planet was in when each one struck, Drabin said. The Chicxulub impactor struck a carbonate platform on Earth, which released sulfur into the atmosphere. The emissions formed aerosols that caused a sharp, extreme drop in surface temperatures. And while both impacts caused significant die-offs, hardy, sunlight-dependent microorganisms in shallow waters would have rapidly recovered after the S2 impact once the oceans filled back in and the dust settled, Drabin said. Life during the time of the S2 impact was much simpler, she said. Consider brushing your teeth in the morning. You might eliminate 99.9% of bacteria, but by evening, they have returned. Ben Weiss, the Robert R. Schrock Professor of Earth and Planetary Sciences at the Massachusetts Institute of Technology, was intrigued by the geological observations of the spheral beds in the paper, which he believes are allowing researchers to explore Earth's ancient impact record the way astronomers can study the surfaces of planets, like Mars. Weiss was not involved in the study. There are no impact craters preserved on the Earth today that come anywhere near in size to what has been inferred to have produced the rocks studied here, Weiss said. Of course, what is special about our record is that, however fragmental and incomplete, it is the only record we can currently study in detail that can tell us about the effects of impacts on the early evolution of life. It's also impressive that despite the very local nature of these observations, outcrops in a small region in South Africa, we can start to understand something about the global nature of these giant impact events. The rocks in the Barberton-Machangwa Mountains are opening up a whole new line of research into Earth's history of impacts for Drabin and her colleagues. We aim to determine how common these environmental changes and biological responses were after other impact events in early Earth's history, she said. Since the effect of each impact depends on various factors, we want to assess how frequently such positive and negative effects on life occurred.